So this video will serve as a review of chapter 4.3. 4.3 reviews types of machines. So we've already talked about a bunch of the simple machines, just kind of in passing about how they work, why they make the force greater, the output force greater than the input force by manipulating distance. In general, there are 6 types of simple machines. There is the lever, the inclined plane, the wedge, screw, pulley, and wheel and axle. This might get divided over 2 videos depending on how long each one of these takes, but we'll go through each of the 6 kind of talking about what they are, what they're used for, and then how they change the mechanical advantage, right? How they manipulate that output force. So the first one, and one that we've talked about a bunch, is the lever. We talked about the lever when we were talking about the paint can and the screwdriver. Right, we use that paint can, or we open up the top of that paint can using the screwdriver as a lever. So it's a simple machine that has a bar that pivots from a fixed point, and that fixed point is called a fulcrum. So this right here, this triangle right here, would be the fulcrum. The lip of the paint can that you rest the screwdriver against, that would be the fulcrum. So there are different classes of levers, which is based on where you put the fulcrum. So if the fulcrum's in the middle here, if the fulcrum's closer to the input force, or if it's closer to the output force, that's going to change the type of lever. So there are 3 different lever types, first, second, and third class. So a first class lever is the fulcrum is between the input force and the load. So this is the load where the output force goes up. This is the input force, so the fulcrum is in the middle. It always changes the direction of the force, right? I push down, this goes up. Can decrease the force used or increase the distance based on the placement of the fulcrum. So here are 3 examples of basically where, how much I can move this fulcrum. So if the fulcrum is closer to the load than the input force, so if I move the fulcrum actually over here, it has a mechanical advantage of greater than 1. So it'll be 1 plus, right? It could be 2, it could be 3. It depends on how close you get it to the output force. Because if we have the, if here's my lever, come on, pen, thank you. If here's my lever, here is the load that is going to be going up, here's my input that's going to be down, and the fulcrum is over here. I am actually going to be able to move this piece here a greater distance because it is closer over to the load, to the output force. So the closer I move the fulcrum to the load, the more I can move the input force. And if I'm moving the input force a greater distance, that means that the output force will be a smaller distance and therefore greater force. If it's perfectly in the middle, like right here in this picture, it has a mechanical advantage of exactly 1, meaning it doesn't multiply. There is no mechanical advantage of like 2 or anything like that. It's going to just be exactly 1. So I push down with 1 Newton, it goes up with 1 Newton. That makes sense because this is only going to travel down, let's say 1 foot, and this will travel up 1 foot. Right? So if it travels up and down the same quantity, then the distances are the same, so the forces are going to be the same. So the fulcrum is in the middle, mechanical advantage of exactly 1. Right? This is 1 plus, meaning at least 1, if not like 1.2, 1.3, 4, or 5. Here it is exactly 1. If you have a fulcrum that is closer to the input force, so it's going to be moved over here. It's got a mechanical advantage of less than 1, but the distance increases. For instance, if any of you are thinking about doing rowing or have done rowing before, you know that as you pull on the oar, you move that oar a relatively short distance, but it travels a great distance in the water. So you're actually putting a greater force on the oar than the output force in the water. However, your goal is to move the boat a very great distance and to glide it forward with each pull of that oar. So you want the oar in the water for the farthest distance. You're kind of having to reverse how we think about this here because you want to be moving that oar the greater distance in the water. So if you're trying to move a big heavy rock, you're not going to pick Option 3, you're not going to have that fulcrum close to the input force because you're not going to be able to move that big heavy rock. It's going to be less than 1, right? So it's going to be 1 minus. You would pick at least this one, if not definitely this one up here, right? Because you are going to have a mechanical advantage of greater than 1. Okay, so all based on where this fulcrum is going, that's going to change the mechanical advantage of these first-class levers. A second-class lever, the load, see, as you see here, it's kind of odd. The fulcrum is way over here, right? You are inputting the force over here, and the output force is going to be right here. So this would be like with a wheelbarrow, right? Imagine this is the wheel of the wheelbarrow. This is kind of the, I don't know what you actually call that. It's the barrow part. It's where you put the rocks or the dirt or whatever you're moving. And this over here would be your handle, right? You grab here, you move the handle up 2 feet. The actual load only moves up maybe 6 inches or something like that. But it is you're able to pick up a 400-pound or a 300-pound load of rocks in the bottom of that wheelbarrow. Whereas if you tried to just reach your hands around the base of that wheelbarrow and pick it up on your own, you wouldn't be able to do that. So the mechanical advantage is greater than 1 because the distance increases, right? I have to pull this, I grab the handles and I move it up, let's say 2 feet. This load doesn't move up all that much. It maybe moves up off the ground like 6 inches. So because of that difference in distance, that's the force distance trade-off, you're going to have a much greater output force. So this is like a wheelbarrow. A third-class lever, you've got the input force in between. So this is where you are loading it, in between the output and the fulcrum. If the fulcrum's over here, this is the output force, and you are the one pulling up here. They do not increase the force because they actually increase the distance that you have to pull on. So this is the example of the hammer, right? Or the bicep curl. You are not actually... it's similar to rowing in this case, but the input and output force are swapped here. So in this instance, you are actually increasing the distance of the output force. So the output force is going to be smaller. So this would obviously not be used to pick anything up, but it's instead used to apply a force over a greater distance, such as a hammer or something like that, when you're trying to nail something in. So pulleys, we've got a couple different types of pulleys. We've used pulleys in the solar cars. You saw them in the transmission lab, so you have a general idea of kind of just how they work. They've got a grooved wheel, and the groove is important so that either a rope or a rubber band can fit through that pulley, right? This would be in our solar car rather. This would be the rubber band, right? So there's 3 general types. We've got a fixed pulley here. It's attached to something that doesn't move, like it's attached to a bar or it's attached to the ceiling or something like that, right? This is not going to move. So what it does is it changes the direction. So this changes direction, and that's it. It doesn't change the mechanical advantage because it's not changing the distance. I pull the rope down a foot, and it goes up a foot. So if the distances are the same, the force input and output aren't going to be any different. So it's just changing the direction. That's still very helpful if you need to move something up and you're on the floor. So a movable pulley, on the other hand, you still have it attached to something immovable, right, up here, but then it's strung through the pulley, which is down at the bottom. So this does not change the direction. I'm standing up here, and I pull this going up, and the input force is then going to be moving this way, and the object also travels up. So it doesn't change the direction, but the mechanical advantage, MA equals 2. Here the MA just equals 1. Okay, so this does not change the direction, but it multiplies the mechanical advantage, or the force, by 2. The block and tackle, so this is this one here, still attached to a fixed object, but then you have a whole number of pulleys, and every pulley that this winds through here is going to multiply the mechanical advantage. So we have 1, 2, 3, 4 rope segments, 4 pulleys, And that means that the mechanical advantage is going to be 4. Meaning that for every single pulley, essentially, you are going to have the mechanical advantage multiplied by an additional 1 times, right? Because they're not only movable, like this option here, right? These are all going to be moving, therefore changing the distance that the rope travels, but you're also adding multiple pulleys, and therefore that's going to increase the mechanical advantage. Here we've got 1, 2 rope segments, and look, mechanical advantage is 2. We've got 4 over here, 1, 2, 3, 4, because we've got 4 pulleys, therefore the mechanical advantage is also 4. So most times in a car or something like that, you're just going to see a fixed pulley, right? You just need to change the direction of the input and output force. But if we're trying to move objects, move things up and down, move things across a room, something like that, you're going to use movable or block and tackle pulleys because those are going to give you a greater mechanical advantage by changing the amount of rope that you pull. So in order to move an object, if the mechanical advantage here is 4 times, if I need to move an object 1 foot, that's going to mean that I need to pull on 4 feet of rope. Right? If the mechanical advantage is 4, that means the distance it's going to travel of the input versus output force is going to be 4 times different. So if I need to move that object 1 foot, I need to pull 4 feet of rope through the block and tackle. Just something to think about to keep relating it back to that force distance trade-off. So the wheel and axle, you've used these all the time. You've used them in doorknobs, you've used them with wrenches, a steering wheel in a car, or a faucet handle. So essentially, you put a small input force to the wheel, right? Here is your wheel. And on the center, like we can imagine this is a steering wheel. In the center of that steering wheel, a part that we don't really think about, is there is an axle within there that then turns. So you move your hand this whole distance, right? You move the wheel a full 360 degrees, which if you're actually measuring how long the distance is that your hand travels on the wheel of the car, you're probably moving, 2 feet in distance. And while your hand 2 feet, your axle down here is only going to travel something like 2 inches. So if there's a much shorter distance traveled by the axle in here, that means that that axle is going to move with much greater force. If you turn the steering wheel of a car, you don't have to put that much force into it. However, think about how much force it takes to turn this little axle, which then goes through a couple other mechanisms and then turns the wheels of the car while you're traveling down the highway at 50, 60 miles an hour. So the fact that you can turn a car that's moving 60 miles an hour and weighs a couple thousand pounds is due to this whole mechanism here, that I can move the steering wheel 2 feet, whereas that little axle turns in its diameter, in its circumference 2 inches. And that's going to multiply that force by 24, right? Because 2 feet is really going to be 24 inches. It's going to multiply it by 12. Whoops, my math is off. But you see, that's why we use the metric system. So it's going to multiply it by 12. So whatever force I put onto the steering wheel will then be multiplied by a factor of 12, because this little axle in here turns 12 times less, so a 1/12 of the distance, but with 12 times the force. So let's take a couple look at the pictures here. So this is, a faucet, right? Here is your input force. Your hand's going to travel around this. And down here, inside this casing here, there's a small little axle that's going to turn just a little bit. So to figure out the mechanical advantage, you're going to take the radius of the wheel and divide it by the radius of the axle. So whatever the radius is right here, from this point to this point, and the radius with that point and that point. So effectively, like we were talking about, is it's comparing the two circumferences, or the distance that will be traveled around, right? Because radius will be connected to circumference, as you've learned in math class. So we've got a couple more to get through, but this is the end of this video. We'll finish that up in 4.3 video 2.